this video, we're going to take a look at section 8.2 on testing a claim about a proportion. In the previous video on section 8.1, we talked about the components of hypothesis testing, but we only looked at them separately, like one component at a time. And while I did use a common problem for many of those steps, what's going to be different in this section is we're going to be given a problem and told to test a claim without those prompts. We just have to go through the entire process from start to finish rather than piece by piece like we did in the previous section. So let's review those components of hypothesis testing. First, we will identify the claim and write it mathematically. We're going to write it in symbolic form. Identify the null and the alternative hypothesis from the claim. Identify alpha and whether the test will be a left tail, right tail, or two-tail test. Calculate the test statistic. Determine the critical value and or the p-value. Draw the initial conclusion, which is to either reject or fail to reject the null hypothesis. And then state the claim about, state the final conclusion about the claim. All right. So, requirements for testing claims about a population proportion. Now, the questions in the homework aren't really going to try to catch you on these requirements. So they're not going to give you a problem and say, test this claim, and then after you do all the work, say, oh, haha, you didn't realize that they weren't simple random samples, and so that you shouldn't have done that. So you're not really going to be tested on these, but I still like to provide this information with the maybe unrealistic idea that perhaps you will find yourself in some situation where you want to test a claim using statistics. And you have to realize that testing these claims only produce valid results if certain requirements are satisfied. So these are pretty much given as satisfied in the problems that we're going to be taking a look at. But in the real world, if you wanted to test a claim about a population proportion, you would want to make sure I almost said the same thing twice. You would want to make sure that these requirements, you want to make sure that these requirements are satisfied. Otherwise, you can go through the process, but if these requirements aren't satisfied, the results are questionable. I don't know why I'm having so much trouble talking today. All right, so first, simple random sample, right? So the sample data has to come from a simple random sample. The conditions of a binomial probability distribution are satisfied. So remember, there was 4 of those. See if I can recount them off the top of my head. 2 possible outcomes. That's the one that always comes to mind first. 2 possible outcomes, which we label either a success or a failure. The trials have to be independent. There has to be a fixed number of trials, and the probability of a success cannot change from trial to trial. So you want to make sure all those requirements are satisfied. And the conditions that n times p is greater than or equal to 5 and n times q is greater than or equal to 5 are both satisfied. This is very similar to the requirements for the confidence intervals that we saw in chapter 7, where we were told that for your sample, you had to have at least 5 successes and 5 failures. That's really what this is asserting, but the numbers are not from your sample, they're from the population itself. So you have to have a sample size big enough so that the given population should have produced at least 5 successes and 5 failures, right? And that's how you would check that mathematically. By doing so, the binomial distribution of sample proportions can be approximated by a normal distribution. So I'm sorry you can't see that. Let's scroll up here. With the mean equal to n times p, which we saw from the chapter 5, the binomial distribution, and the standard deviation equal to the square root of n times p times q. Which, by the way, I hadn't really considered that before. But if you take the formula for the z-score and you plug these into that formula, that's how you develop the test statistic that we use for testing these claims. So it actually kind of ties in really nicely with things that we've done previously, the z-score and the binomial distribution, mean and standard deviation. When you put those together, it produces the test statistic that we will use, which is this formula here. It takes a little bit of finagling to get it in that form, but this is derived from the formula for a z-score by plugging in the mean as n times p and the standard deviation as the square root of n times p times q. So I thought that was kind of interesting. All right. So this is the test statistic that we should use when we get to that phase of the problem. P hat, which is the sample proportion, minus P, which is the assumed population proportion. Again, we don't really know what that is. That's what we're testing a claim about. But for the sake of argument, we assume its value based on the null hypothesis, right? So we take the null hypothesis we're given, assume that it's true, and that's the number that we plug in there for the value of P, divided by the square root of P times Q over N. Remember, Q is 1 minus P, and again, P is a value that we get from the null hypothesis. N is the sample size. So that's where you get all those numbers from. Plug them in there, and that gives you the test statistic, which we will use to make a determination as to whether we should reject or fail to reject the null hypothesis. In order to make that decision, though, we want to compare it to a standard, if you will. And so we will compare that to the critical value to decide if the test statistic is too extreme or if it's kind of an ordinary test statistic. And where we draw the line is the critical value. You can also convert the test statistic to an area, which is called the p-value, and then compare that to the alpha that's provided in the problem. All right, so I'm maybe getting a little bit ahead of myself there. So let's do an example where we actually go through all those steps in detail. Based on information from the National Cybersecurity Alliance, 93% of computer owners believe they have antivirus programs installed on their computers. In a random sample of 400 scanned computers, it is found that 380 of them, which is 95%, actually have antivirus software programs. Use the sample data that we just talked about from the scanned computers to test the claim that 93% of computers have antivirus software. Use a significance level of 0.01. So again, now on paper, we're kind of just left to our own devices here, and we have to kind of remember the components and to how, the order we have to go through those components. On MyStatLab, they do still kind of walk you through it. So, the first part will be what's the claim, and you have some multiple choice options. Once you get that right, or once you miss it enough times, then it gives you the null hypothesis, gives you those options. So it kind of does walk you through it. But be aware that when you take the exam, especially, again, I don't know what the future might hold, but currently these exams are available on Canvas, and they're typed out by the teachers. They're not just imported from MyStatLab. And for this is what your test question will look like. And there's no prompts. It doesn't say, what's the claim? What's the null hypothesis and the alternative hypothesis? So you'll kind of need to remember the steps you need to go through in order to complete the problem to test the claim. Right. So now I'm saying there's no prompts. I'm thinking about there might be some, I don't know. But you should know the process, especially by the time you take the test, because even though this is kind of new at this point, we're going to do this again in 8.3. We're going to do it again in 9.1. We're going to do it again in 9.2. The details change, but the steps are the same every single time. So hopefully by that time you'll feel pretty comfortable with, okay, I know what to do. Claim, hypothesis, alpha, and whether it's a left tail, right tail, or two tail test, test statistic, critical value or p-value, reject or fail to reject, and then state a final conclusion. All right, so start with the claim, right? So let's do that. First step, step one, the claim here, which is that 93% of computers have antivirus software, right? So that's a proportion they're making a claim about. And it's not that it's less than 93% or at least 93%. It's exactly 93%. So it's an equals to. So the claim is that the population proportion is equal to 0.93. That's the first component. That's phase one, if you will. Phase two is to use that claim to construct the null and the alternative hypothesis. We had some practice doing this in section 8.1, the previous video. So we're just kind of reviewing it again here. Remember the criteria. The claim has to become one of these hypotheses. The null has to have equals to in it. And then the alternative and the null need to be opposites of each other. So essentially it comes down to, if the claim has equality, then it becomes the null hypothesis. Right? It has to. It can't become the alternative, because then you can't satisfy the last option, which is that they're opposites of each other. Or you can't satisfy the second option, which is that the null has equality in it. So the only way to satisfy all three of those is if the claim has an equals to, the claim becomes the null hypothesis. So we get P equals 0.93. Right. Now the alternative hypothesis has to be the exact opposite of that. The exact opposite of equals to is not equals to. All right. And so there is our null and alternative hypothesis. Phase 3 is determine alpha, not determine it, but find it, identify it, because it's always given to us in the problem. You just, now let me say this, if it's on the test and it's a test that I typed up and alpha's not there, it could be an oversight on my part. Sometimes I forget to put the value for alpha. Of course, if it's in class, raise your hand, but if you're at home, like if you're testing remotely, like in the math lab or at home through the Respondus monitor or whatever, and you need a value for alpha and I didn't give you one in the problem, please, by all means, pick a value for alpha. You can pick whatever you want. Pick something, typical like 0.01 or 0.05, but pick something so that you can actually still do the problem. So if I forget to put an alpha in there and there should be one and there wasn't one given, then feel free to choose your own value for alpha. But if I've typed the questions in correctly, you should be given this value for alpha. And I know for a fact on my stat lab, they will always give you the value for alpha. You never have to pick it yourself. All right. So alpha is 0.01. This will be a two-tail test. So again, we talked about the reasoning in the video for 8.1, but the shortcut is you just look at the alternative hypothesis. If it's not equals to, it's a two-tail test. All right. 4, let's find the test statistic. I don't know why I did this. I do a fancy T for math, like if it's a variable. I never do it when I'm just like writing out a word. So I have no idea why I did that as a fancy T, because you can see my other ones aren't like that. Test statistic. Maybe I was thinking of like t-value, but that's not what we're using here, right? The test statistic in this case is a z-score. Z equals p hat minus p over the square root of p times q divided by n. So p hat was given to us in the problem. And actually, this is a very nice thing that was done for us. They give us the number of successes, 380. Out of the sample size, which is 400, right? So this is n right here. I didn't write that in a very good spot. Let's try that again. This is the value for n, and this is actually the value for x. So there was no reason that this had to be done for us. But whoever wrote this problem, it wasn't me, I just copied it, but whoever wrote this problem was nice enough to actually do the calculation for us. But sometimes that won't be the case. So remember, p hat is the number of successes in the sample divided by the sample size, which would be 380 over 400 in this case, but we were already told that's going to be 95%, which is going to be 0.95. So I really didn't need to do this part. It was already done for me. But I wanted to illustrate that because probably on a future problem, it won't be done for us. We'll have to actually do this calculation ourselves. Right, so there's p hat. The value for p, that's the population proportion, which, again, in reality, we don't actually know. But for the sake of argument, to test this claim, we are going to assume the null hypothesis is true. And so I'm going to assume it's actually equal to 0.93. I don't have any evidence for that yet, but I'm going to assume that. In fact, that's what we're testing, right? We're testing whether p is equal to 0.93. So let's just assume that it is. And then compare that to the sample statistic, the sample proportion, and get this z-score based on those two things. And then we can make a judgment as to whether that seems like a sound assumption or not. Right? Now, if p is going to be 0.93, then q is going to be 1 minus p, which will be 1 minus 0.93 in this case, which is going to be 0.07. So that's the value for q. Again, the value for p shows up again here. It's the same thing, 0.93. And then n was equal to 400. So now we have all the numbers we need to calculate this z-score. It's going to be 0.95 minus, looks like I'm going to need a little more room here, 0.93 divided by the square root of 0.93 times 0.07 over 400. All right, so that is my test statistic. So I have to dump that into my calculator, let the calculator do the calculation for me, and I'll have my test statistic. parentheses around the numerator. Again, on paper, you don't need this, but in most calculators, you do. So 0.95 minus 0.93 divided by the square root of 0.93 times 0.07 divided by 400. And technically, we would probably need to have parentheses in the denominator, except the square root kind of keeps it all together for us. So you shouldn't really need that in the calculator. As long as your square root has parentheses, that kind of puts all that together there. I'm sorry, I don't know why it's not writing. Let's see. Okay, maybe it is. I just can't see it. Okay. So I'm sorry. It just kind of bugged me that it didn't. I just feel like I'm making it worse now. Let me just kind of. Oh, I don't want to rewrite everything though. That's going to take too long. Let me erase. Sorry, this just really kind of bothered me all of a sudden. Okay, there. That worked out pretty good. So this really, I want to make sure to have it go all the way down so that it's incorporating the denominator. I don't want to be misleading on the screen. Anyways, I'm wasting time. Z equals 1.57. My stat lab should tell you how far to round. If I don't on the test provide those directions for how far to round that, I'm just going to leave it to your judgment. And I'll be flexible. So I might decide to round it 2 decimal places. Maybe I'd say 1's maybe cutting it a little short. But you know, if I go 4 decimal places, but you only go 3, I'll probably just let that go. I think 2's kind of enough for a z-score. And this is a fairly ordinary z-score. So again, initial impressions here, without seeing what I'm going to compare it to, 1.57 isn't really that extreme. So the assumption doesn't look that unreasonable. If I got a z-score of like 2.5, that's kind of extreme. That makes the assumption look unreasonable. Then I'd start to doubt this assumption, which means I probably would end up rejecting the null hypothesis in that case. This doesn't make me want to reject this null hypothesis. It just doesn't seem that extreme given this particular z-score here. And so I'm guessing we're going to fail to reject the null hypothesis. But to know for sure, we want to have something to compare this value to decide if it's too extreme or if it's ordinary. And that's what the critical value is for. So that's the next phase, critical value. So let's do that down here. Or p-value. Now, on the test, unless you are specifically asked for both the critical value and the p-value, you really only need one of these to draw your conclusion. So on the test, if I don't specify, feel free to use either one, whatever your preference is. If you like using critical value, you can just find the critical value. You don't need the p-value. If you like using the p-value, you can just use the p-value. You don't have to bother with the critical value. You just need one of these in order to actually finish out the problem. But on my stat lab, I'm pretty sure the directions ask for both. It'll ask you for critical and p-value. And so you have to find both, even though you just need one of those to draw a conclusion from. So for critical value, what we want to do is take the value of alpha, which is, what am I trying to do here? Change the color, which is 0.01. And it's a two-tailed test. So for a two-tailed test, we have to take alpha and divide it by 2 for the critical value. So 0.01 divided by 2, which is going to be 0.005. Excuse me. And then we're going to draw a picture. And for a two-tailed test, that alpha has to cover both tails. That's why we're dividing it in 2, because half of it will go in the left tail. Half of it's going to go in the right tail. And then we want to find the z-score corresponding to that area on both tails. So we actually have 2 critical values here. There's 2 z-scores we're looking for. And so to do that, we're going to find inverse norm. The area to the left is 0.005. And that's going to give me my critical value for my left tail. And we use the symmetry to kind of cheat our way to the other one. So the critical value in the right tail will just be the same number, but positive, right? So I really don't have to do this calculation once, even though I'm looking for 2 different numbers here. So inverse norm, 0.005. And I get negative, so this is going to give me negative 2.576. Right. That's the critical value that's in the left tail. 0 is right dead center in the middle. So the critical value in the right tail for that same area will be positive 2.576. So those are my 2 critical values. So there's actually 2 in this case. Right. For the p-value, what you want to do is take the test statistic, draw a picture with that, and then find an area that corresponds to that test statistic. Right. So 0's in the middle, which means the test statistic, it's positive, so it'll be to the right. And the area that you want to look for, you're either going to find the area to the left or the area to the right. If it's a left tail test, you find the area to the left. If it's a right tail test, find the area to the right. If it's a two tail test like it is in this case, find the area to the closest tail. So for 1.57, it's closer to the right tail than it is to the left tail. So I want to find the area to the right. I want to find the area in that right tail. So I'm looking for that area right there. And to do that, I will use normal CDF because we're using the normal distribution. The lower bound there is 1.57. Now here's where I could get myself in some trouble, and I don't really double check myself on this. So I really probably should at least one time do this calculation from a problem that's on MyStatLab and then plug it in to make sure that I'm giving you sound advice. Because I'm like, oh, round it. Of course, if you round it as far as I keep saying Math Excel. If you round it as far as MyStatLab tells you to round it, then you should be okay. I would think you'd be okay. But I have seen cases where you round it here to type it in as your answer on MyStatLab. And then when you use the rounded number later for the p-value, it might not be right because it's rounded off. And you want to really use the full decimal expansion of that z-score. Hopefully it's not going to be too picky. So my advice would be, if you're rounding it off like I am to 2 decimal places, and you're getting the answer wrong, maybe what you should do, now there's various reasons why it might be wrong. Maybe you're finding the wrong area. Maybe you're typing something else in wrong. But if you have a suspicion that it's because you're rounding, go back, recalculate the test statistic, and don't round it. Keep all the decimal places, and then try it again. And if that gives you the right answer that time, then okay, we can't round this much, right? At least on MyStatLab. On the exam, like I said, I'm a little more flexible, maybe too flexible about it, because I know some teachers are kind of picky about that because, it's a matter of, how much precision should we keep for these numbers? Based on the situation, I kind of don't worry about that as much as maybe I should. So the upper bound is infinity, right? Goes forever to the right. And we don't need degree of freedom because it's the normal distribution. So normal CDF, 1.57. Again, I'm not plugging this into MyStatLab, so I hope that's okay, but there's no way for me to know if MyStatLab would be okay rounding the z-score that much. So that's something you're going to have to kind of test the waters on when you're doing the homework. Okay, so I end up getting from this 0.0582. Maybe I'll go one more decimal place. 1. All right. Now, that is not my p-value, because if it's a two-tail test, then you have to take the area that you get from normal CDF using that number and double it. You have to multiply it by 2. So only for the two-tail test, you have to double the area that you find from your test statistic. If it's a left-tail test, you don't double it. If it's a right-tail test, you don't double it. But for a two-tail test, whatever you get for the normal CDF needs to be doubled. So I multiply that by 2, and I get 0.11. I'm just going to go 4 decimal places this time, 64. Right. Hopefully that is accurate enough to be valid on MyStatLab if this problem was on there. Okay, so that's my p-value. Okay. Next, we will draw a conclusion. Again, there's 2 ways you can draw this conclusion. So this is phase 6. So you can either use the critical values. So think of it like this. And we have our cutoff scores here at negative 2.576 and positive 2.576. And that's where I'm drawing the line. If my test statistic is more extreme than these values, I will reject the null hypothesis because it's a bad assumption if we're getting such an extreme result. Because it's probably not really extreme, it just looks like it's extreme because of the assumption that we were making. If it's between these two numbers, then I don't think it's extreme, and so therefore I will not reject the null hypothesis. I will fail to reject it. Right. So our test statistic actually is in between. It's right here. It's 1.57. Right. And so that's clearly between those two critical values. And so I will fail to reject. I don't know what's wrong with me. I did this earlier, kind of like with the inverse norm. I put in and then I was going to put I. I don't know why I'm getting those switched around. And I did the same thing here. I put the L before the I. So fail to reject the null hypothesis. And again, we talked about that in a little bit more detail in the previous video. So please feel free to go back and look at that if this wasn't an adequate enough explanation. I explained it in a little more detail in the previous video. For the p-value, we compare the p-value to alpha. In this case, the p-value is 0.1164. The alpha was 0.01. The p-value is greater than alpha. If the p-value is greater than alpha, same conclusion. You fail to reject the null hypothesis. Only if the p-value is less than alpha do you reject the null hypothesis. All right, and so now we're ready to state our conclusion about the claim. And we want to do this in words without any mathematical jargon. So in this case, failing to reject the null hypothesis, remember, the null hypothesis was the claim that was being made. So this conclusion I'm wording is about the claim itself, not about the hypotheses. It's about the claim. But whatever I say about the null hypothesis, I'm saying about the claim because those are the same statements, right? So any conclusions I draw about the null hypothesis immediately apply to the claim that was being made. If I fail to reject the null, I am failing to reject the claim. All right. So the proper wording for the conclusion is as follows. There is not sufficient. Actually, I think what I did last time is I typed it out because I just don't think I can write. I'll just keep stop. Like, look at those F's. They're horrible. I have to stop and erase, and I'd have to do that a bunch of more times. So let me type it out. There is not sufficient. And I think they put sample evidence, but I think it's just okay to say evidence. There is not sufficient evidence to warrant rejection of the claim. Right? We're failing to reject the claim. We fail to reject the null hypothesis. We're failing to reject the claim. So there is not sufficient evidence to warrant rejection of the claim that the proportion of computers with antivirus software, I'm saying this kind of funny. The claim that 93%, I don't need to use the word proportion, 93% of computers have antivirus software. I think this sounds better if I put it that way, right? But you want to make it a complete sentence using, I'm putting 93% in there, but you have to refer to that number in some way or another. But we are not using math jargon whatsoever. We're not using hypotheses. We're not using p-value, critical value, none of that stuff. It's just plain language conclusion about the claim itself, complete sentence, and with detail, right? So you don't want to just say there's not sufficient evidence to warrant rejection of the claim, right? Be specific what that claim actually was. What is the thing that you are unable to reject, right? Now, that doesn't mean the 93% value is true. We just don't have evidence to show that it's false. So one thing that kind of bothers students, I didn't really go into this in the previous video, but you can never prove a null hypothesis. You can either show it's false or you fail to show it's false, but you can never prove it's true, right? And for the alternative, it's the reverse. You can never prove the alternative hypothesis false. You can only prove it's true. So if your goal is to actually show a statement is true, you want it to become the alternative hypothesis. So if it was really our goal to show that 93% of computers have antivirus software, we should have worded the claim in a way where that became the alternative hypothesis. So we might say there can't be equality, right, for it to be the alternative. So we might want to say something to the effect of that more than 93% of computers have antivirus software. Then the claim becomes greater than 93%. That becomes the alternative. And then we can have a chance of proving that true. But if it becomes the null, the only thing you can do with that claim is to either prove it's false or be unable to prove that it's false. Now, if you're unable to prove it's false multiple times, so you keep attacking it and you keep showing that we couldn't show it was false here, we couldn't show it was false here, we couldn't show it was false here, that collection of evidence starts to point to the direction that maybe it's true then, because you've tried to show it's false multiple times and you continually are unable to show that it's false. That lends some evidence, how do you want to say, that lends some weight to that claim maybe being true. So if you try to test it 10 different times and all 10 times you are unable to show that it's false, that's pretty strong evidence that it's probably a true statement. But the process itself would never draw that conclusion. You can only either say the claim is false or we're unable to show it's false if the claim becomes the null hypothesis. So that's just kind of the structure that we're working with, and that's the limitations that we're working with. So if you want to prove a statement false, if you really feel like, oh, I think this is a false statement and I want to show it's false, you need to word it so it becomes the null hypothesis. If you want to show a statement's true, you need to word it so it becomes the alternative hypothesis. All right, let's move on to the next example. The drug Symbicort is used to treat asthma. In a clinical trial of Symbicort, 18 of 277 treated subjects experienced headaches. Test the claim that less than 10% of treated subjects experienced headaches. Assume a significance level of 0.05. So, speaking to what I was just saying, perhaps this drug company wants to prove something true about Symbicort, right? But maybe they want it to be true that few people experience headaches. And they want to be able to make that claim that our study proves that less than 10% of people experience headaches. They maybe want to make a positive statement in that regard. So again, if they want to prove something like that true, they need to word the claim so that it becomes the alternative hypothesis. And then there's a chance that if the numbers work out right, they will end up proving that statement to be true. If they worded this to say that the claim, or if they said something to the effect that the claim is that 10% of people got headaches, exactly 10%, then that becomes the null hypothesis. And then the only thing that could happen from that is either it will be false or they're unable to show that it's false. And maybe that's not the kind of conclusion they want to share in their marketing, stuff. So they're wording this in such a way that it becomes the alternative hypothesis so that they hopefully will be able to show that it's true, that they can say the tests show that less than 10% of people get headaches when they're treated with this drug. All right. So anyways, let's go through the hypothesis testing process. Step 1, what is the claim? In this case, I don't know why I'm putting equals to there. We put colons. That works better that way. Is that the proportion is less than 10%. Right? Less than 10. So far, these problems have been fairly nice in their wording. I don't know. You might argue with me on that last one because it didn't say the word equals to. Sometimes they'll even do that just to make it as easy as possible on you, like for translating it into math. This one was pretty direct, right? But sometimes the wording can be a little bit hard to figure out. For example, they might say, test the claim that the majority of people experienced headaches. Well, majority, you have to, infer from that means greater than 50%. And I've seen some other ones that are kind of oddly worded that make it a little bit difficult to translate the claim into a mathematical form. But so far, we've been pretty lucky with these claims. They've been fairly literal. But just warning you, so the reason you might say, why did I even bring that up? Just to kind of warn you that you might have a couple of homework problems. There shouldn't be too many, but maybe a couple where it's not so literal and you have to try to infer from the wording what the claim should be. All right. Next step, phase 2, the null and the alternative hypothesis. Again, the claim should become one of these statements. The null hypothesis must contain equality. So if this claim has to be one of these two, it can't be the null because it doesn't have equality. So it must become the alternative hypothesis. Right. And then the third thing is these need to be opposites of each other. So the opposite of less than is greater than or equal to. So those are exact opposites of each other. And by taking the opposite of less than, you get the equality that you're supposed to have in the null hypothesis, right? So the less than becomes the alternative hypothesis. Then when I go to take the opposite for the null, it will introduce the equals to in that statement. And then now the null satisfies that requirement that it has equality in it, right? Now this is, I went over this in the last video. This is really traditionally how we would word the null. I know word doesn't sound right. This is traditionally how we would construct the null and the alternative hypothesis. But in recent times, they have adopted a new approach, which is to always have the null become equals to. So my adjustment to that has been to stick with the old method like we just did here. And then once you've constructed the null and the alternative, then I call this simplifying. We're going to simplify it to just equals to. So the null becomes that p simply equals 0.10. And the alternative doesn't change. It stays the same, right? P will be less than 0.10. And so this is the answer that you would want to select on MyStatLab. So this is the way it needs to be formatted to get the right answer on your homework. However, that being said, again, going back to the testing, if I'm giving you the test myself, like I typed up the problems and I'm going to be grading it by hand, then I would be perfectly happy if you just left it like this. That's fine with me. I'll accept either answer. Either way is fine. All right. Phase 3 is to identify alpha, which in this case is 0.05. And whether it's a left tail, right tail, or two tail test, the shortcut is to look at the alternative hypothesis. It's a less than, which means this will be a left tail test. All right. And so that's all there is to phase 3. Phase 4, test statistic. I'm not going to write it out. I'm just going to go ahead and find it. Same formula as the previous problem. We have p hat minus p over the square root. See if I can write it correctly this time. P times Q over N. Right? So we need to go find all this information. Remember, the value of P will be found with the null hypothesis. That sounded kind of weird. Sometimes I have trouble deciding what prepositional phrases to use. So I'm like, do I say with, in, at? You know, all those maybe could possibly work to some degree or another. But the value of P is found with the null hypothesis. That sounds really weird to say. Now I'm like overthinking it, I think. We assume the null hypothesis is true. And that is how we get the value for P. And then that means the value of Q will be 1 minus that, 1 minus P, which is going to be 1 minus 0.10, which means Q is equal to 0.90. So that'll be the value of Q. N is the number of test subjects, which is 277. So this is the value of N right here. And then P hat is the sample proportion, which this time they weren't nice enough to calculate for us. We have to calculate it ourselves. So X is 18. That's the number of successes over N, which is the sample size. And that would be P hat. And you might be tempted to say, okay, plug that into my calculator. Let's see what that is as a decimal. And that might be kind of nice to have an idea of the percentage, right? To compare it to 10%. You know, what's the actual percent in the sample compared to 10%? But for the purposes of, again, and I know I kind of did a bad thing in the last problem, but for the purposes of, you know, getting a precise enough answer, it's better just to keep this as a fraction. And that way you're using the exact value. So when you do this calculation, you'll get the answer you're supposed to get. So I was a little bit cavalier about rounding in the last problem, and I'm still going to be a little bit cavalier about it here, but at least to get the test statistic, I make sure all the numbers that I put in the formula are as precise as possible. Once I get the test statistic, then I kind of start rounding things and I get a little bit careless after that. So Z, but I adjust, right? I might be kind of careless, but if I was doing the homework and I found that I keep getting the wrong answer, I'm off by just a little bit here or there, then it's a rounding issue. And then I would adjust. I would make sure not to round as much as I go through the homework. And so you should do the same, right? Okay. So P hat was 18 over 277, keep it as a fraction, minus P, which is 0.10. I know it's weird to have decimals and fractions mixed like this, but it's for the best, for right now anyways, over the square root of P, which is 0.10, times Q, which is 0.90, over N, which is 277. And so we plug that into our calculator and we get our test statistic. So again, we need parentheses in the numerator, right, in order to make sure the calculator will do this correctly. So 18 over 277 minus 0.10, close the parentheses, divided by the square root of 0.10 times 0.90 divided by 277. Close the parentheses on the square root, and I end up getting negative, and it's okay. Test statistics can be negative. I don't know how often that's happened previously, but that is a thing. So it doesn't mean you did anything wrong. Negative 1.94. I'm going to go 2 decimal places again. I hope that's okay for finding the p-value. All right, so negative 1.94. Now this one's kind of on the fence. This is why you need a critical value to make a comparison to. You need to have some like rigorous way. And what's important about the critical value is it's based on an alpha, which again measures how often we will get false negatives, I think. I can't remember which one. One's alpha, one's beta. But again, it's all like quantified, which is important, right? And so we'll use alpha to get a critical value to help us make a decision here, because remember, -2 is where we start to consider a z-score unusual. Like that's the rule of thumb. This is very, very close to that. So it's right on the fence of really being an unusual value. But is it, how extreme is it? How important? The alpha kind of dictates how serious we are about how extreme this needs to be before we reject the null hypothesis, right? So the smaller the alpha, the more serious we are about this really needs to be seriously extreme before we're willing to say that the null hypothesis is false. A bigger alpha is a little bit more relaxed. It's like, okay, we'll let it go, like it just kind of makes it easier to reject the null hypothesis if the alpha is bigger. All right, so this one, it's hard for me. So again, this is just initial impressions. It's hard to really tell where this is going to land. It could go either way. It really depends on alpha. So this is kind of the z-score where for one value of alpha, we're going to reject the null hypothesis, but if it's a different alpha, we'll fail to reject. It's just right there in that area where it could go either way. Okay, so let's find out which way it's going to go in this problem. So the next phase, number 5, I will find the critical value. In this case, there will just be 1. So it's a left tail test. So all of the alpha goes into the left tail. I'm sorry, I'm doing all this in the same color. So this will be 0.05, all in the left tail. None of it goes in the right tail. We're not concerned about the right tail this time. Just the left tail is the area of concern. So all of the alpha goes into the left tail. And then we will find the z-score that corresponds to that area in the left tail. We'll do that by inverse norm. We'll type in the alpha, 0.05, which is the ending, because I really haven't had time to edit. But the last video I think I did, I watched it, and there was a part where I froze up. And it was, so I noticed like, I just froze again. Okay, that my webcam freezes, but the audio still plays. Like there's a little hiccup in the audio, but then it still plays and you can hear me going, what's going on, but then my webcam is frozen. So I apologize for that. I don't know if it's humorous or annoying or what it might be. All right, so inverse norm, 0.05, which is the area in the left tail, area to the left. And so I get a z-score of negative 1.645. All right, so that's my critical value. All right, now it's a little weird because the critical value is a z, the test statistic is a z. And so we usually try to distinguish between those by like putting a subscript of alpha on the critical value. So that's the z-score that corresponds to alpha. The z by itself is your test statistic from your sample, right? And maybe, I don't know, we'll talk about it in a second, but I'm not going to comment on it just yet. But you can make the comparison and see what conclusion you should draw. So again, we don't need the p-value. We know, like from the numbers we have now on the screen, we can make our conclusion. We can make our decision. But I'm going to wait to do that. But I also want to talk about, I keep just repeating the same phrase over and over. I want to talk about p-value because, I want to make sure you know how to do that as well. So even though I don't technically need to do both of these, I think you're asked to do that on the homework and just so that you know how to do the problem either way so that you can make a decision which way you prefer to do it. And then on the test, just go with your preference. either critical value or p-value. You don't have to do both. Right, now for p-value, what we're going to do is take the test statistic, zero's in the middle, so the negative 1.94 actually is going to be closer to the left tail. And then we want to find the area, in this case, to the left. Not because this is closer to the left tail, but because it's a left tail test. No matter where the test statistic is, you find the area to the left. That's what you do for a left tail test. Right, so the area to the left is going to be this area here. I'll do normal CDF. The lower bound this time is negative infinity. The upper bound is negative 1.94. Again, we're using a rounded number there, so hopefully that's not going to give us too imprecise of a p-value. But what I end up getting is normal CDF, negative, I do 99999 for negative infinity, and then negative 1.94. And I'm getting a p-value of 0.0262. I might be going too many decimal places here, but that's the value I get. Now, if you use a more precise z value for your upper bound here, for your test statistic, if you didn't round it to the second decimal place, but let's say you went to the fourth decimal place, your answer might be a little bit different than this one. And in fact, better than my answer, because mine would be more imprecise because I use less decimal places. This is more likely to be an imprecise answer. Not more likely, but if I'm using less decimal places, it's definitely less precise than if you had used more decimal places. So you might kind of want to experiment with that. Maybe try keeping 4 decimal places here and see what kind of difference it makes. I don't know, maybe I should go ahead and experiment with that. So let's see. Okay, so this time with more decimal places, I get 0.0260. Right, if I go 4 decimal places. So you see, it makes a difference at the 4th decimal place. But before that, it's the same. So if MathXL is asking us to round to 4 decimal places, now sometimes they'll build in a tolerance where they kind of give you a little bit of wiggle room on your answer. But if they're being picky about it, if I'm rounding this to 2 decimal places, I'm not going to get the right p-value. My p-value will be wrong at the last decimal place. So if you're finding that, okay, I typed this in, it was wrong, I kept, trying different things, and then you get to see the right answer, and it says this is the right answer, but this is what you had, that's a rounding issue, because you see it's really close, it's just wrong at the last decimal place. It's because I'm rounding too much here. So let's go ahead and scrub that one out. We'll keep this one. That's the more accurate one. We do not need to multiply this one by 2 because it was not a two-tailed test. So that's your p-value right here. All right, I'm sorry that I went on a tangent there. Okay, and it wasted time. I might just delete some of that out. I don't know. See, the problem is with editing, it takes time. Like I edited a couple of videos recently, and if the video is an 1.5 hour recording, it takes about an 1.5 hour to edit it because you have to kind of watch the whole thing again. So that's, instead of an 1.5 hours on the video, I'm spending 3 hours on one video, and I just don't have time to do that at this time. So maybe once I get all my videos recorded and things kind of settle down and I don't have other tasks I need, because we're trying, with the whole pandemic thing, we're having to move other things online. We're just having to make adjustments in every area of how we do our job. And that takes quite a lot of time to do. And so I'm trying to save time wherever I can, but maybe once things kind of settle down, I can go back to these videos, edit them, re-upload them. But for now, I'm just going to leave them as they are. So what do I do here? Do I reject or do I fail to reject? So if you use the critical value to decide, then the cutoff that we've determined from the critical value is negative 1.645. And so if it goes further into the left tail past this number, we reject because it becomes, if it's past this number, it's too extreme. So we have to reject the null hypothesis. If it stays on the right-hand side of this number, anywhere over here on the right-hand side, we fail to reject. And when I say it, sometimes I'm sorry I do that because that's really imprecise. I'm talking about the test statistic, right? If the test statistic is further into the left tail, we reject the null hypothesis. If the test statistic stays anywhere over here on the right-hand side, we fail to reject. Our test statistic was negative 1.94, which is further into the left tail. It's right here. So we will reject the null hypothesis this time. Right. So that will be our initial conclusion. If you want to use the p-value method, the p-value, compare that to alpha. The p-value is 0.0260. Alpha is 0.05. And we can see from this that the p-value is less than alpha. If the p-value is less than alpha, reject the null hypothesis. All right, so our final conclusion about the claim, I'm going to type it out this time instead of trying to write it, is that, let me grab my keyboard here, there is sufficient evidence to support the claim that, because remember the claim was that less than 10% of subjects had headaches. What we rejected was the null hypothesis, which was the opposite of that. Remember, the null hypothesis was evidence to support the claim that less than 10% of subjects taking Symbicort had headaches. I guess that's a good enough complete sentence. All right. So going back to look at the actual null and alternative hypothesis. So the claim was that P was less than 0.10. That became the alternative hypothesis. The null became the opposite of our claim, right? And that's the thing we're rejecting. We are rejecting the claim that the proportion is greater than or equal to 10%. That's what we reject. We're saying that is a false statement. The data that we have suggests that this is false, that the null hypothesis is false, and that P actually is not greater than or equal to 0.10. If P is not greater than or equal to 10%, then the alternative must be true, right? The opposite must be true. The opposite being the claim that we were testing. So I don't know if I said that. I feel like I kind of butchered what I was saying there. So let me try to say it one more time, right? We are rejecting the null hypothesis. We're saying this is false. We're saying P is not greater than or equal to 10%, which means the opposite of that is what must be true. The opposite of greater than or equal to is less than. We're saying that P must be less than 10% since it's not greater than or equal to 10%. And the claim, this was the claim, right? The claim was that P is less than 10%, and we are saying it's true that P is less than 10%. So by rejecting the null, we are supporting the alternative hypothesis as true. And it's the alternative hypothesis that is our claim. So whatever we say about the alternative hypothesis in this case, we are saying about the claim as well. By rejecting the null, we are supporting the alternative hypothesis, which means we support the claim. And that's why the final conclusion is such. There is sufficient evidence to support the claim that less than 10% of subjects taking Symbicort had headaches. Okay, the Genetics and IVF Institute conducted a clinical trial of the Y-sort method designed to increase the probability of conceiving a boy. As of the writing of this problem, I guess maybe would be a good way to say it, 291 babies were born to parents using the Y-sort method, and 239 of them were boys. Use a 0.10 significance level to test the claim that the Y-sort method is effective in increasing the likelihood that a baby will be a boy. All right, so let's go through the process again. I'll stop all my commentary and let's just focus on getting the problem done. So the claim here is that, so this is one of those, I'm going to my commentary again, where it's not very literal. The claim is not like literally spelled out for us where we can easily translate it into math. It's saying the claim is that this method is effective. So then we have to infer from that wording what it means mathematically for this method to be effective. So if this method wasn't effective, what percent of the babies would you expect to be boys? You would expect it to be 50%. If the method has any sort of effect, then the proportion of boys that are born would be more than 50%. So now, if you only get like 51%, that's not very effective, but it's more effective than just random chance, right? And so it's not a high threshold here. If it's more than 50%, the method is considered effective. Whether it's practical or not is another question, right? And so the claim here is that the proportion of boys should be more than 50% if this method is actually effective, right? And so that would be the claim. But again, it doesn't spell it out for you, right? It doesn't say test the claim that the proportion is greater than 50%. We have to infer that from the wording that's provided. So I kind of warned you about it earlier in the video, and I didn't realize, because this is really kind of the first time I'm going through this material, that one of the problems would actually illustrate that thing that I was talking about. Anyways, 2, hypotheses, null and alternative. This is kind of the same as the last problem, except it's a greater than, but same idea. There's no equality here, so the claim has to become the alternative hypothesis. The null will have to be the opposite of that, which is going to be less than or equal to. And then we simplify it to just equals to, right? So we're going to have p equals 0.50. And for the alternative, we don't make any modifications. It'll still be greater than 0.50, right? So this is what we're going to go with as our hypotheses. Step 3, oh, sorry about that. I thought I switched to move the screen. Let's try that again. 3, let's change the color up here. The value of alpha in this case was 0.01, I believe. And this time we are going to have a right tail test, right? Because this is a greater than. That's going to make this a right tail test. 4, we'll find the test statistic. We have z equals p hat. Let's try that again. P hat minus p over the square root of p times q over n. The value of p is, I'm struggling with the wording again. I don't know why. We assume the null. I'm just going to, I feel like it's easier for me to say if I just say it in this direction. So we're going to assume the null hypothesis is true, and that will give us our value of p, which is 0.50. Right? And so q is going to be 1 minus that. It'll be 1 minus p, which will be 1 minus 0.50, which is also going to be 0.50. So that's the value for q. That's what will get plugged in there. N is 291. It's this value here. That's the value for n. And then p hat is the sample proportion. And so that's going to be based on n, but also x, right? So there's 291 altogether in the sample. 239 were boys. That's our value for x. So p hat's going to be 239 over 291, which, again, resists the urge to get the decimal version of that number. Keep it as a fraction because that keeps the value exact. And so we'll just leave the value of p hat as 239 over 291. And we'll plug all these numbers in. Let's see, I guess I'll just kind of move over this way, and I will plug the numbers in right here. So p hat is 239 over 291. Minus p, which we assume to be 0.5. That's from the null hypothesis. So I wanted to keep it all on the screen, but I guess we got the number we needed already from p hat, so we don't need it on the screen anymore. Over the square root of p, which is 0.50, times q, which is also 0.50, divided by n, which is the 291. Again, we'll put this in parentheses for typing it into our calculator. So parentheses 239 over 291 minus 0.50 divided by the square root of 0.5 times 0.5 divided by 291. Close the parentheses on the square root, and we get this value, which really jumps out at me as a really extreme value. 10.96. Hopefully that's, again, 2 decimals. Maybe I should do 3 decimal places just to be safe. That way we can feel relatively certain that our p-value is right to 4 decimal places if our test statistic is accurate to 3 decimal places. So there's our test statistic. 10.9, almost 11. That is really, really extreme. So I think sometimes students will get this calculation and they'll say, oh, z is equal to 10. Oh, that's interesting. You're like kind of just not really think anything of it. But remember, the normal, again, I shouldn't use the word normal. The ordinary z-scores are from -2 to 2. Those are your typical data values. Anything that goes beyond -2 and 2 is extreme. So 2.5 as a z-score is extreme. A z-score of 3 is extreme. A z-score of 5 is really, really extreme. So 10 is just unbelievable. Like that, it's a very, very rare occurrence. Z-scores just should never be that big of a number. So I know the number 10 doesn't seem like that dramatic of a number, but for Z-scores it is. It's a very dramatic Z-score, right? So that's very extreme. No matter where we decide to draw the line, this is going to cross it. I mean, that's just so extreme that no reasonable line that we would draw for where we should divide the ordinary values from the extreme values would ever include 10 as an ordinary value. That just would never happen. So I can already tell from this that we are going to reject the null hypothesis. I mean, that's such an extreme value. But even though I kind of know how this is going to end, we should still go through the formal process because we want to do it in a legitimate way, right? And to legitimize it, you have to get alpha, you have to do critical values and show, right, that this is more extreme than whatever critical value that you find. And go through the formal process to draw your conclusion. So, all right. So, phase 5, critical value. In this case, we'll only have one because it's a right tail test. And we will take this value of alpha, since it's just a right tail test, all of it goes into the right tail. And then we want to find the z-score that corresponds to that area in the right tail. Now I'm going to do inverse norm because that's what you have to do. But the thing that I'm going to do that's maybe a little bit, it's not unorthodox, but it's not technically correct. So the area in this tail, let me go ahead and write that down here, is 0.01. For inverse norm, you actually want the area to the left, not the area to the right. So for this z-score that I'm trying to find, the area to the right is 0.01. Inverse norm wants to know the area to the left in order to do the calculation. However, a shortcut here is that we can still just use the area to the right. And this only is true if you're finding a z-score. If it's not a z-score, like in chapter 6, we were actually using inverse norm to find data values. And this trick wouldn't work in that section because this only works with the assumption that 0 is at the middle and that this is symmetric. And if you're doing other kinds of data values, then 0 is probably not the middle value. And so you can't use this symmetry trick to get the answer, right? But because we're doing z-scores and 0 is always the middle value for the z-scores, I don't know if I'm really using very good terminology there, but z-scores in the middle of that symmetry, right? Then the value that I would get by using 0.01 actually gives me this value over here, which will be negative, but I know that number will be the same over here. It'll just be positive. So it's sort of a shortcut that we can use, that a lot of students like to use actually. So what I end up getting from inverse norm is 0.01. It comes out negative 2.326. I'll just go 3 decimal places. But because I know this is in the right tail, I'm going to drop the negative sign. I know this is the right number, but to be in the right tail, it needs to be positive. So what I really found, the reason it came out negative is because I was actually finding this value over here with this area being 0.01. But because of the symmetry, I know this number will be the same number, but positive. And so that's what I'm doing there. And again, I'm not actually putting this alpha in the left tail. I'm just saying what I actually calculated with this inverse norm was this number here. But the symmetry tells me that it'll be the same number, but positive for the number I'm actually looking for. All right. So hopefully I didn't confuse you with that. But it's a nice shortcut. Now, if that shortcut is confusing to you, then the thing I should have done here was inverse norm, and the area I should have used was 0.99. Because that's the area to the left of this number. So I take 1 minus this to get the area to the left, and then I do inverse norm with that area, and then it comes out as positive 2.326. You'll get the same number, but it'll be positive like it's supposed to be. All right, for p-value, we are going to find the area that corresponds to the test statistic. It's a right tail test, so we want the area to the right. And so we're going to use normal CDF. The lower bound is 10.962. The upper bound is, I'm going to put infinity. I was about to put 99999, but technically it's infinity. But in my calculator, I'm going to approximate that with 9999999, a bunch of nines. And let's see what we end up getting here. So normal CDF, 10.962, comma, 9999, a bunch of nines. Right. And I get a very, very small number, which just goes to show you how extreme of a z-score this is. So my calculator tells me 2.98 times 10 to the negative 28. Right. And so that's 0.000000298. Whoops. Oh, I hate when I do that. Sorry about that. If the screen kind of jumped on you. And for some reason I can't see my cursor. Oh, there it is. Okay. So let me scroll over so I can make the point I want to make here, which is that's going to be 27 zeros there. Right. To the negative 28th power means you have 27 zeros before you hit the 298. And so if they ask us to round the p-value, which is pretty common, they'll say round it to 4 decimal places, round it to 5 decimal places, round it to 3 decimal. I don't know how many they're going to say. If they ask you to round this at all, it's just going to round to 0. So while the p-value isn't literally 0, it's so small that it's practically 0. And so when you round it, the answer ends up just being 0, and that's what you'll probably type into MyStatLab is the p-value is 0 in this case. But technically it's just a hair, just a shade above the number 0, but not much. All right, so that's the p-value. Let's draw our conclusion. All right. So if we use the critical value to draw our conclusion, we're drawing the line at 2.326. That's where we're drawing the line between ordinary z-scores and extreme z-scores. Right? Anything that's bigger than that goes further to the right, is considered extreme. Anything that stays to the left of it is considered not extreme, is considered ordinary. Right? Our test statistic, now again, when I keep using this very vague language, and I really have tried to stop saying it, right? If it goes this to, if it's further to the right, I shouldn't say it. I'm talking about the test statistic, right? So if the test statistic is further to the right than 2.326, it's extreme, and we have to reject the null hypothesis. If the test statistic is anywhere to the left of that, then it's not extreme, it's ordinary, and we will not reject the null hypothesis. But it is very, very far to the right of this, right? 962, sorry. So it's over here, further to the right, more extreme than 2.326, so we will reject the null hypothesis. Right. For the p-value, we compare the p-value to alpha. The p-value is practically 0. And alpha is 0.01, so the p-value is less than alpha. In that case, we reject the null hypothesis. Right? Either way, we're rejecting the null hypothesis. So why don't you pause the video for a second and think about what the final conclusion should say. Okay, so the final conclusion should state there is sufficient evidence to support the claim that the gender selection method is effective in increasing the likelihood that a baby will be a boy. So again, the second half of that sentence, the wording is flexible. It doesn't have to say exactly the same words that I just said. But the first half is not flexible. It needs to pretty much say exactly what you see there. And it's the same scenario that we encountered in the previous problem, right? Our claim became the alternative hypothesis. And we went on to reject the null, which means we support the alternative, which is the claim. That's what happened in the previous example, and it's the same thing that just happened here. So that's why it's the same conclusion, right? But we just, again, the scenario is different, so the wording's a little bit different on the second half of that sentence, right? So you could also have said something to the effect of, there is sufficient evidence to support the claim that more than 50% of babies born will be boys, or something to that effect. So you can bring the 50% in there if you wanted to, but I'm just using the wording that was used in the original problem for the claim. So that concludes the video on section 8.2. I will see you in the next video on section 8.3.